Hello guys, in today's class we shall discuss about open delta or VV connection. Like we have seen in the previous class that a single three-phase transformer, if one of the windings get failed, then whole transformer has to be put into the service. There you may have power interruption, so reliability is not that good. Again, the winding has to be replaced, again they have to put into the service, so it takes time. So if I have three single phase transformers connected in delta-delta connection, then also what power can be supplied? Mainly it is used in the mines. But coming to this topic, that is open delta or VV connection. So here even the transformer bank has two single phase transformer, then also you can enjoy three phase supply by making such connection. But at the cost of reduced efficiency or reduced kVA. Let us see how much kVA is reduced. Say out of 3 transformers, if you are using only 2 transformers, then as per in layman's language it will be of 2 by 3. Yes or not? Means 2 by 3 transformers you are using out of 3 transformers. 2 by 3 is nothing but how much? It is around 66.67 something. Yes or not? Means you are using at 66.67% of kVA of the total transformers. But in actual it is not so. It is not 66.67, it is something else. Let us see why it is not 66.67 and why it is something else in coming derivation. So by making such connection, you can give three-phase supply to this two single-phase transformers, as well as you can take three-phase supply out of these two single-phase transformers, but at the reduced efficiency or reduced kVA. So this is what the phasor diagram we have. If I remove one of the single-phase transformer, it is same for primary as well as secondary. So like I told you, it is not 2/3. Yes or not? It's not 2/3. It is around 57.7%. If I do 2 by 3, if I take percentile of that, means I will get what? 66.67 something. But here it is not so. It is actually you are supposed to use 57.7% of the total kVA. Okay, like if you are having 1 kVA transformer, then it will be what? 57.7% of 1 plus 1 plus 1, that is totally 3 transformers are there, right? Because 3 transformers will make you delta connection, but since you are using VV connection, so you have to make use of only 57.7% of the total kVA. That is total kVA is how much? Total 3 transformer means if each transformer is having kVA rating 1 kVA, then it will be 3 kVA, right? So 57.7% of 3 kVA is your total kVA available from the transformer. Let us see how this 57.7% has come. You may get the question, why the load for VV bank is only 57.7% of the total kVA of the transformers. It can be proved by as follows. Let us take a normal healthy delta-delta connection. You can see this is the primary side and this is the secondary side. Like I told you, this current whatever flows here, it is line, and whatever current flows in delta part is called as delta current or phase current. And again, delta current as well as phase current as well as line current are not same, as current getting divided here. So I phase equal to IL by root 3 or IL is equal to root 3 into I phase, whatever you can call, both are same. But here line voltage as well as phase voltage are both same. Now coming to this, I have, let us say this transformer has become faulty and I have removed from the delta-delta connection. Same with respect to primary as well as with respect to secondary. I have removed. Yes or not? Yes. Even though if I have removed this, I can give three-phase supply to these two single-phase transformers, and I can take three-phase supply out of this two single-phase transformer, thus making VV connection. So one thing remained same here, that is phase voltage and line voltage remained same. But what about phase current and line current? Are they remaining same here? No. Why? Because current was used to divide as soon as it come here, as soon as it comes here, current used to divide. So that's why the formula I phase equal to IL by root 3 or IL is equal to root 3 into I phase. But here, is current getting divided here? No, current is not getting divided. So whatever current is flowing here, the same current flows in the phase current, that is phase of your one of the transformers. So what I can call here is IL is equal to I phase. IL is equal to I phase. It is true for this case also. It is true for this case also. Current is not getting divided here. So technically, if you see properly, means it is almost like star connection. So that's why the reason this IL is equal to I phase. Since anyhow neutral is not there, so that's why the reason V phase is equal to VL. Okay. So hope you understood this. Why IL is equal to I phase? The reason why we are calling IL is equal to I phase, because current is not getting divided here, right? So whatever it is with respect to primary, same it is for secondary side. Now we shall take the first figure, that is this one, 2.81 A, whatever it may be, primary or secondary. We know that for delta capacity, we know that power formula is what? Root 3 times VL into IL. Yes or not? We are ignoring the power factor and all. So just it is what? Root 3 into VL into IL. If you write in terms of V phase, means it will become what? 3 into V phase I phase. Okay. Anyhow they are written in terms of line. Okay. So it is what? Root 3 into VL into IL. Better you remember in this fashion. But in the delta capacity, we know that IL is equal to root 3 times of I phase, or I phase equal to IL by root 3. Any formula I can remember. So that's why the reason why I have replaced IL by root 3 into I phase. Okay. So after multiplying root 3 into root 3, it becomes what? 3. So delta capacity, we have got one more formula, that is 3 into VL I phase. Anyhow VL is equal to V phase, you can either replace VL is by V phase also, there is no problem. Like I told earlier, you can write in terms of 3 V phase I phase, yes or not? So both are same. Okay, either if you remember this or remember this, both are same. So delta capacity formula is what? 3 times VL into I phase. Now coming to the second figure here, for VV capacity. You can see for VV capacity, again the formula remains same, root 3 VL into IL. See, this formula is traditional formula which remains always same for any 3-phase transformer. So root 3 VL into IL. But now see what we have got formula for IL as well as I phase. Anyhow the current is not getting divided, so what happens? IL is equal to I phase. So I am replacing IL by I phase. Before it was what? IL is equal to root 3 times of I phase. Why? Because current was dividing in the delta connection of the transformer. But here in VV capacity, current is not dividing. So whatever IL is there, same I phase will be same. So IL is equal to I phase. So I'm going to replace IL by I phase. Now what I'm going to do is I'm going to divide 2.82 by 2.81. That is this VV capacity by delta capacity. VV capacity is what? Formula root 3 VL I phase, whereas delta capacity is what? 3 VL I phase. Yes. Okay. Now VL gets cancelled as well as I phase gets cancelled. So finally what I get here is root 3 by 3. You can write root 3 by 3 in another format, that is 1 by root 3. So if you do 1 by root 3 means it will be 0.557, or it is what? 55.7%, or if you want to round off means it will be around 58%. So VV capacity, that is VV capacity, whatever in terms of kVA, will be equal to what? 58% of delta capacity. Yes, if I take delta capacity here, that is cross multiplication, then VV capacity, whatever kVA rating of VV capacity will be, should be what? Should be 55.7% or 58% of the delta capacity. That is what I told you. If a single phase transformer is of 1 kVA rating, then totally altogether capacity will be what? 3 kVA. So VV capacity equal to what? 58% of 3 kVA or 55.7% of 3 kVA. That whatever the answer result, that much only you have to load that transformer. If you load above it, then transformer will be overburdened. So heating starts to take place if you overburden it. Okay, hope you understood this, all of you. Right? So VV capacity is how much? It will be 55.7% or 58% of whole delta capacity. That's why it is not 2/3, that is 66.7%. Yes or not? Hope we have it is not just number we are telling, we are proving it by equations, right? That 2 by 3 what happens, it will be in terms of layman's language, right? So okay, even if it is layman's language, it is wrong now, yes or not? Because it is not 2/3, it is not 66.61%, it is 55.7% or 58% of the total delta capacity. Okay, so that's why it is given, it is not 66.7%, it is 55.7%. So reduction in the rating can be calculated as follows. I told you in layman's language we understood that it is around 66.67, but as a matter of fact it is around 55.7%. So total reduction in terms of actual reduction is how much? 15.476. Just you subtract 66.67 minus 50, actually it should be 57.7. okay, so just subtract there, they have made a mistake here, it should be 57.7. so if you take in terms of 57.735, then actual the total reduction is how much? 15.476 in terms of actual reduction. Okay, just for your remembering sake. So in case, let us say that if let us assume your bank of 3 single phase transformers are connected and you have applied full load to that. Okay, yes or not? If you have delta connection, then you can apply full load as per your kVA rating of your transformer, right? Yes. Let us say if one of the transformers fail, that is, if one of the transformers become open circuited, then what happens? Then there will be overload on transformer, yes or not? Then there will be a overload on transformer, on each transformer. That overload can be calculated like this. So total load in VV, we know that it is root 3 VL I phase, yes or not? In this already we know that, yes or not? And again, if I want means I can convert in terms of I phase into IL, because anyhow phase current and line current are both same, yes or not? Again, VA per transformer is how much? So it is VL into I phase. So VL I phase is get cancelled. So root 3 will be the answer. So root 3 is 1.732. So total load on VV transformer will be, it will be 1.732 times that of VA per transformer, cross multiply. That is around 1.7 times, that is can call it as 173%. Yes or not? 173.2%, that much of voltage ampere, that is VA rating of transformer will be increased. Increase in sense what? That much of burden will be put on each of the transformer if you say one of the transformer get fail in the bank of 3 single phase transformers. Okay. So to avoid that, what you can do is you can reduce the load. As per our calculation, you can put it to 57.7%. Totally there is two way of remembering this 57.7%, that is available kVA. How is that? It is 57.7% of total kVA of the transformer. Here they have assumed as each transformer has rating of 100 kVA. So all three transformers together will have rating 300 kVA. So that's why they are multiplying 57.7% of 300 kVA, which results 173.1 kVA. This is the one method. Second method is what? It is 86.6% of available transformers at the service. So how many transformers are at the service now? After removing one transformer, out of 3, if I remove one means there will be totally 2 transformers available. So 2 transformer in sense what? 200 kVA. So 200 kVA into 86.61%, it will result again same of as of the earlier, that is 173.1 kVA. Let us see utility factor now. It is defined by the ratio of operating capacity of transformer in VV capacity, that is in VV connection, divided by available capacity of transformer in VV. So we know that operating capacity of transformer is how much? It is around 57.7%, yes or not? And again available capacity is how much? Totally 2 transformers means it is 66.67%, yes or not? So 57.7% divided by 66.61% would result me 86.6% or 0.866. Okay.